Welcome to section 8.3, where we are going to be looking at the concept of annihilators in their use in solving differential equations. So in the previous sections, we looked at how to solve differential equations that were homogeneous, so they were set equal to 0. In this section, we have L of y equal to f, so we have this non-homogeneous solution to the differential equation. We want to be able to solve more general problems like this, not only ones that are equal to 0. In order to solve a differential equation like this, we have a few steps. The first is to solve the corresponding homogeneous differential equation. So first things first, we will let the right-hand side be 0 and solve that using the methods we saw in the previous section. The general solution to this is called the complementary function, abbreviated y sub c of x. So we're going to find the general solution to the corresponding homogeneous differential equation. Then we're going to find one particular solution to the differential equation equal to f. That particular solution will be abbreviated y sub p. And our final answer, the actual solution, will consist of both of these parts. So it's y sub c of x plus y sub p of x. So we take the complementary plus the particular. Okay, so that's the solution to the homogeneous differential equation plus the one particular solution that corresponds with f. Now, in order to find that particular solution, what we need to do is we need to find an operator that when we apply it to the function, it turns the function into a 0. So really, our solution to solving a differential equation that's not equal to 0 is by taking the part that is equal to 0, and then to solve the part that's not 0, we're going to make something make it 0. So we're kind of revolving around, zeros here a lot. But this operator, that when we apply it to the function f, it becomes 0. This type of operator is called an annihilator, which probably sounds a bit cooler than it actually is, but it is called an annihilator because it essentially annihilates this function. It turns that function into a 0, so it makes it become nothing, essentially. So we can apply annihilators to a function to turn it into a 0, and then use that to solve that particular solution. So a couple quick examples before we look a little more in depth at this. If f of x was equal to x squared, we would use the annihilator d cubed. So because we know, so since f triple prime of x, that would be first derivative is 2x, second derivative is 2, third derivative is 0. So f triple prime of x is 0. D cubed applied to f would be 0, because remember, the d is the derivative operator. So this is just saying take the third derivative of this function, okay, which the third derivative of that function here is, of course, 0. So this would be an annihilator for that function. Similarly, we have if f of x is sine of x, we use the annihilator d squared plus 1. So if we took d squared plus 1 of sine of x, that would be the second derivative of sine of x, so that's negative sine of x, plus just sine of x, right? So no derivatives taken there. Negative sine plus sine is 0. So this would be an annihilator for that function. Now, we have annihilators for a bunch of different types of functions. We're going to take a look at the list at the top of the next page. So these are all the annihilators and properties that we're going to be working with in here. So the annihilator of an x to the k function is d to the k plus 1. So basically, whatever that highest power is, we take the derivative, that power plus 1 times, and that'll turn it into a 0. This also would include like plus any lower terms. Because if we had if this was like x cubed and we had x squared and x to the first or something like that, if x cubed is getting turned to 0, these ones will also become 0 first. So we don't have to worry about the lower terms. The annihilator of e to the ax is d minus a. We can start combining different functions. If we have x to the k times e to the ax, that annihilator is d minus a to the k plus 1. The annihilator of cosine of bx and sine of bx is the same, actually. It's d squared plus b squared. The annihilator of e to the ax cosine of bx and e to the ax sine of bx is this expression. So that's d squared minus 2ad plus a squared plus b squared. And the annihilator for the expression with x to the k times e to the ax times cosine of bx or sine of bx is essentially just kind of a combination of their separate annihilators. So we've got d squared minus 2ad plus a squared plus b squared, all raised to the k plus 1. So these annihilators are not something that you will have to memorize, but this table is here for your reference, and we will be using this for all of our annihilator examples here. One additional note: if you have a function that is the sum of different types of functions, then the annihilators just multiply. So we would just combine them and apply them to the different functions separately. So for example, just a couple quick examples here. If we had x squared plus e to the 7x, the annihilators that we would use for x squared, it would be d cubed. And for e to the 7x, it's going to be d minus 7. And because they're being added, we multiply these factors. So this is going to be our annihilator for this function. For a function like this one, so we've got x cubed minus sine of 3x plus x e to the 2x. So we'll go one term at a time here. For x cubed, it'll be d to the 4th times, for the negative sine of 3x, so we get, sine of bx is d squared plus b squared, and that's 3, so 9. And for x e to the 2x, so that's this form right here. So that's x to the first, e to the 2x. So that's going to be d minus 2 to the 2. So d minus 2 squared. And that would be the annihilator for this function. So if we were to apply this annihilator to this function, it would turn the function into a 0. That would then allow us to solve the differential equation in that way. So let's try an example actually solving a differential equation. So solve y double prime minus y equals 16e to the 3x. So we're going to start off with step 1. So remember, step 1, we find that complementary solution. So we solve the corresponding homogeneous system. So y double prime minus y equals 0, which if we go ahead and put that in our derivative operator notation, that's d squared minus 1 of y equals 0. And then we go ahead and we convert this derivative operator notation to our auxiliary polynomial and then set up our auxiliary equation. So that's where we take r and replace it for d. So we get r squared minus 1 equals 0. So we get r equals negative 1 and 1 for our two values. This is going to give us our complementary solution here. So remember, the general form of the solution is e to the rx. So this is going to be c1 e to the negative x plus c2 e to the x. And I'm not going to box it because that's not the final answer, but that is definitely going to be part of the answer. So highlight that there. That's our complementary solution. Then for step 2, we're going to look at the function. So for 16e to the 3x, the annihilator, so a of d, that we're going to use, we have e to the ax. That's going to be d minus 3. So we have d minus 3. So we can start with kind of the original form in the derivative operator notation. So that was d squared minus 1 of y equals 16e to the 3x. We're going to apply this annihilator to both sides of the equation. So we get d minus 3 times d squared minus 1 of y equals d minus 3 of 16 e to the 3x. And by definition, the annihilator will turn this part into a 0. So we're going to have this expression equals 0. But now we can go ahead and convert to that auxiliary equation again. So this is going to give us r minus 3 times r squared minus 1 equals 0, which gives us r equals 3, negative 1, and 1. So in terms of our particular solution, notice these two values are repeats of the ones that we found up here. So these two are already covered in the complementary solution. We're looking at what needs to be added to the solution, and those two are already there, which means the only new piece of information we have is that r equals 3. So these are already included in yc of x. So our particular solution, we're going to have y sub p of x equals, I'm going to label it a e to the 3x. The reason I'm labeling this one differently is because this is a particular solution. We need to actually solve for the a value here. The general solution, we don't need to solve for those constants. So we need to solve for a. And we're going to do that by finding its derivatives and then subbing it back in to the differential equation. So we know y sub p. We need the derivative of it, which will just bring down a 3 basically. So we get 3a e to the 3x. We also need second derivative. We actually don't even need the first. We just really need the second. That's going to be 9a e to the 3x. So what we get, so our differential equation was y double prime minus y equals 16 e to the 3x. We're going to sub this in for y double prime, sub this in for y. So we get 9a e to the 3x minus a e to the 3x equals 16 e to the 3x. So we have 8 e to the 3x equals 16 e to the 3x. Oh, excuse me, 8a. 8a e to the 3x. So this means for those to be equal, 8a must be equal to 16. So a has to be 2. So we're going to take that value for a in our particular solution. So in this solution right here, we know that a must be 2. And so our final total solution is just complementary plus particular. So we're going to have c1 e to the negative x plus c2 e to the x plus 2 e to the 3x. And that would be the solution to that differential equation, found by, again, taking the solution to the corresponding homogeneous differential equation first, and then finding the particular solution using the annihilators and adding that to the final result. So let's take a look at, we're going to do a couple more examples here. Solve y double prime minus y prime minus 2y equals 10 sine of x. So we'll start with step 1. So we have d squared minus d minus 2 all applied to y equals 0. Because again, step 1, we solve that corresponding homogeneous system first. So we're going to get, by converting this into the auxiliary equation, we get r squared minus r minus 2 equals 0. Which does factor as r minus 2 and r plus 1 equals 0. So r is 2 and negative 1. So that's going to give us our complementary solution. So that's c1 e to the 2x plus c2 e to the negative x. So that's our complementary. Then for step 2, we're looking for the annihilator for this function, 10 sine of x. So if we go back and look, sine of bx is d squared plus b squared. This is just sine of x, so that's sine of 1x. So it's just going to be d squared plus 1. D squared plus 1. So if we apply that to both sides of this differential equation, so that's going to be d squared plus 1, d squared minus d minus 2 of y equals d squared plus 1 of 10 sine of x, which again, that will make 0 because that's why we chose that annihilator. That's how we designed this setup. So we just have this side equal to 0. And now we'll do the same thing. So we'll go ahead and convert this into the auxiliary equation. So that would give us r squared plus 1, r squared minus r minus 2 equals 0. The roots that we get, this one is exactly the same as above, right? It's the same roots. So we still get 2 and negative 1. This one produces 2 new roots, but those roots, however, are going to be imaginary or complex numbers. So, right, you subtract 1 and then take the square root. You get square plus or minus square root of negative 1. So that's going to be I and negative I. So again, the first two are already covered in the general solution. These are the 2 new ones for the particular solution. So we have to think back to how we write our solution when we have complex roots like this. So remember, we have e to the ax, cosine of bx, and then e to the ax sine of bx, because they always come as the pair. So we're going to get a times e to the ax, but a here is 0, right? Because this is like 0 plus 1i and 0 minus 1i, like that. So it'll just be e to the 0, and then cosine of x, right? Just 1x there. And then plus b, and then again e to the 0, and then sine of just 1x. So a cosine of x plus b sine of x. So that's going to be the general form of the particular solution. But with the particular solution, again, we want to solve for these constants. So we need to solve for a and b. So we are going to sub them back into this original differential equation, which means we're going to need the original y right here. So that's yp, need its derivative, and need its second derivative. So let's just get those right here. So that's going to be, so yp prime of x. Derivative is going to be negative a cosine x, and then plus b, negative a sine x plus b cosine x. There we go. So that's y prime. And then we need y double prime. So that's the derivative of this one. So it's going to be negative a cosine x minus b sine x. And now this just kind of amounts to a bunch of algebra, but we sub those into the original differential equation. So that's going to be negative a cosine x minus b sine x minus y prime, so negative a sine x plus b cosine x minus 2 times y, that's a cosine x plus b sine x equals 10 sine x. So if we do some regrouping here, we can regroup by cosine and sine, so kind of separate them off. We end up getting negative 3a minus b times cosine of x plus a minus 3b times sine of x equals 10 sine of x. Now, because we have two variables, we're not just going to have one equation, we're going to have a system. So we're going to have two here. We know that whatever the coefficient is on sine has to be equal to 10. So this will be equal to 10. And with the cosine coefficient, there are no cosines on this side, which means that this has to become 0 in order for these sides to match perfectly of this equation. So this would give us two equations. So negative 3a plus b must be 0, right? So the cosine coefficient has to be 0 to match. And the a minus 3b must be equal to 10, right? Because the sign needs to match. So we've got a system of two equations here. You could set it up using a matrix, but with something this small, we really don't need to. We get a equals 1 and b equals 3. So those are going to be, oh, excuse me, b is negative 3. Did I mix something up here? Let's see. The cosine, negative 1, negative 2, and minus b. Sine, we have plus a, minus 3b. should be, Sorry, I'm just looking over this again. That should match there. Take a look at this again. So this one tells us, so B is 3A. So we get A minus 9A equals 10. Negative 8A is 10. Okay, so no, we're not getting 1 and 3. We're getting some fractions in here. So A will be negative 5/4, and B will be 3 times that. So that would be negative 15/4. Okay. And that should work there, and that will give us the 10. Yeah. Okay. So, sorry about that. So our final solution, now that we know A and B for the particular solution, so we're going to have y of x equals the complementary c1 e to the 2x plus c2 e to the negative x, and then plus the particular solution. A and B are both negative, however, so that's going to be minus 5/4 cosine x and minus 15/4 sine of x. And that will be our solution to that differential equation above. Again, by combining the complementary with the particular. So let's take a look at one more. Solve y double prime minus 3y prime minus 4y equals 15e to the 4x. So start with step 1, which is going to be, so we'll convert this, that's d squared minus 3d minus 4 of y. Solve that corresponding homogeneous equation. Set that up as the auxiliary equation, that's r squared minus 3r minus 4 equals 0, which factors r minus 4 and r plus 1. So we get r is 4 and negative 1. So our complementary will be c1 e to the 4x plus c2 e to the negative x. And just like that, we'll move along to step 2. So we look for the annihilator for 15e to the 4x. So e to the 4x is going to be, it's d minus a. So it's going to be d minus 4. So we're going to get d minus 4 applied to both sides of the differential equation, which the right side will become 0, because again, we designed it that way. So we'll solve the corresponding auxiliary. And again, we do get the same roots here, but now we have a new root popping up. So that's 2, and then 4 and negative 1 still. Oh, excuse me, where did that 2 come from? That should also be 4, or minus 4. Okay, so we're getting another 4. So that's the only new root that we have. So for our particular solution for this one, we have a new root of 4. 4 is already a solution here. So we do have a repeat. And remember, when we have a repeat, we just introduce a factor of x in front of it. And then every additional repeat gets a new factor of x. So this is going to be ax e to the 4x for this particular solution. And then solve for a. So we need the first and second derivatives of this. So yp prime is, gonna need more room for this. Yp prime of x. This is a product, so we do need to use the product rule. The a can stay out in front, but we're left with 4x e to the 4x plus e to the 4x. And yp double prime is the derivative of that, which is itself going to also have a product in it. But we get some combinations of terms. So we get a times 16x e to the 4x plus 8 e to the 4x for the second derivative. So if we now substitute these into the original differential equation, so we're going to get y double prime, so that's going to be a times the 16x e to the 4x plus 8 e to the 4x minus 3y prime, so minus 3 times a times 4x e to the 4x plus e to the 4x minus 4 times y, that's 4ax e to the 4x equals 15 e to the 4x. Which then, if we kind of manipulate this around a little bit, there's an e to the 4x in everything here, so we'll just pull it out to the front. What's left, we have some terms with an x, and then some terms without one. So if we combine the x terms together and the non-x terms together, we would get, so there's 16a minus 12a for this one, minus 4a for the last one, and that's times x, plus, for the terms without an x, that's 8a minus 3a, and that's it, equals 15 e to the 4x. This difference becomes 0. So that whole first term with the x is gone. All we have left is just 5a times e to the 4x. So we have 5a e to the 4x equals 15 e to the 4x. So a is 3. So our solution to the differential equation, we have c1 e to the 4x plus c2 e to the negative x plus 3x e to the 4x. Again, that's our repeated root, and it's our particular solution, so we solve for the 3. So that would be the method of annihilators. Now, if we move into section 8.7, our final section for this chapter, we're looking very briefly at the concept of variation of parameters. So first off, suppose that we wanted to solve this differential equation here. If we set that up using the derivative operator and then convert to that auxiliary equation, we would get r squared minus 12r plus 36 equals 0. We would factor, that's r minus 6 squared equals 0. So we get r equals 6 with a multiplicity of 2. So we would get the complementary solution of c1 e to the 6x plus c2 x e to the 6x because of the repeated root. But now, once we're done with step 1, we need to move on to step 2, and there's a problem. We don't know how to annihilate that expression given our knowledge up to this point. So in order to annihilate f, it is sometimes impossible. Sometimes we just don't have the tools to be able to annihilate a function properly. So in order to handle cases like this, where we cannot annihilate a function, we are going to look at a new method here that can only be applied to second order differential equations. So it is more limited in the scope. It can only be applied to second order, but it is a much more general approach than annihilators. So it can handle a lot more functions than annihilators can, but again, only for second order differential equations. So this method that we have now is called variation of parameters. So we already know how to get the complementary solution. That's fine. What we need now is a process for finding the particular solution. So we're going to, once again, kind of ride the coattails of people who have already figured this stuff out, and we're going to use this as our kind of educated guess, if you will, that this is the general form of the particular solution. So u1 of x, y1 of x, plus u2 of x, y2 of x, where y1 and y2 are the solutions in step 1. Okay, so that's the complementary. So there's y1 and there's y2. And u1 and u2 are going to be defined as follows. So u1 of x is going to be the integral of negative y2 times f over the Wronskian of y1 and y2 dx, because everything in here is in terms of x as a function. And u2 is going to be the integral of y1 times f, also over the Wronskian of y1 and y2 dx. It is possible to derive these formulas. We're not going to take the time to go through that process, but that is something that is doable. So this will be the general form of our particular solution using variation of parameters, and these are the values of u1 and u2. So it's coming based off of the solutions y1 and y2 that we already found in the complementary solution. So like if we look back, we're going to return to this example now. We already found the complementary solution was e to the 6x and x e to the 6x for those two. So what we need to do now is we're going to take, so y1 is going to be e to the 6x, and y2 is x e to the 6x. So those were our two solutions. We're going to need to take the Wronskian of the two solutions. So y1 and y2. So which means we're going to take the determinant, where the columns represent the derivatives of these solutions. So this one's going to give us 6 e to the 6x. This one does invoke the product rule. So we get 6x e to the 6x plus e to the 6x. If we perform that determinant, so AD minus BC, we end up getting e to the 12x for the Wronskian. So we get e to the 12x. That's going to go in both of the formulas here for u1 and u2. So u1 of x is going to be the integral of negative y2. Let me go ahead and just put the negative out in front here. So negative e to the 6x times f. So f is this function on the right-hand side of the differential equation. So that's going to be times e to the 6x over 1 plus x squared, all over the Wronskian, which is e to the 12x dx. Notice what happens here. We have e to the 6x times e to the 6x. That's e to the 12x divided by e to the 12x. So those end up canceling. So we get negative integral of... Oh, I'm sorry. I put the wrong one in here, didn't I? Have you been yelling at your screen this whole time? This should be y2 in this formula. So slight adjustment. There should be an x right here. So make sure that there's an x in that expression. Because now, so this part stays the same. So e to the 6x, e to the 6x cancels with e to the 12x. So we're left with the negative in front with x over 1 plus x squared dx. And this is something we can integrate using like u substitution. So, right, let u be 1 plus x squared. Du would be 2x dx. So divide, get a factor of 1/2. So we get a negative 1/2. Antiderivative will be the natural log of 1 plus x squared. That's the value. That's our value for the integral. u2 of x. So this one will be y1. So that'll be e to the 6x times f. So that's e to the 6x over 1 plus x squared over e to the 12x again, the Wronskian. So that is, again, e to the 12x over e to the 12x. This time there is no x there because we're using y1 this time. So that's just going to be 1 over 1 plus x squared dx, which is kind of like a special derivative or antiderivative, but hopefully you remember it from Calc 1. That's the inverse tangent of x. And we don't need to include the plus c on either of these. So it's a particular solution. We can just let c be 0, so it's not going to show up at all. So our particular solution here, so I'll just do this right here because I want to save room for the final solution. Our particular solution is going to be u1y1 plus u2y2. So that's negative 1/2 ln of 1 plus x squared times y1, so times e to the 6x, plus inverse tangent of x times x e to the 6x. So that's our particular solution in this case. So our overall solution to this differential equation, that's y of x equals complementary plus particular. The complementary was c1 e to the 6x plus c2 x e to the 6x plus this part. So that's minus 1/2 ln of 1 plus x squared times e to the 6x plus inverse tangent of x times x e to the 6x. And that is our process for variation of parameters. So again, this process, when it comes to working with second-order differential equations, can be as effective or more effective than using annihilators. because we can use this even when we don't know what the annihilator would be, or we don't have one. But again, its scope is limited only to second-order differential equations. Anything outside of that, we would need to use annihilators to handle. But that brings us to this end of section 8.7, to the end of our work in chapter 8, kind of reintroducing differential equations and looking at how we can solve several different types.